really be careful of that. So I just want to go over, I just want to finish up today. Today we're finishing up. I'm just going to review in a finishing up type of way of multi-electron electronic structure. But I want to stop, go a little bit further back and get some more big picture. Any of you have any questions about anything? Remember, you have a homework due Wednesday. No assignment after that. I may or may not have homework 11. No questions? We're all okay? All right, so big picture. As I review multi-electron wave functions and things like shielding, remember that, shielding, let's see. We started out with, okay, I have, this is the separated form of the hydrogen Hamiltonian. It's already got the angle parts taken care of, so this is like this, it's whittled down into the radial form. It's been whittled down by the whole separation technique. And I can tell because all the angle parts have been removed to just, it's like here's a rotational energy. It just gets thrown in there. And all of this is fine and good. Now, remember that there's a bit of weirdness that I've got the angle parts and the radial part in the same term, and that still confuses me. Maybe you remember that when it comes to solving all of this jazz, it all comes down to separability, and remember the technique for separation and whatnot. And this one's a little funky because I have an R squared and some angle bits, but regardless, the result is separable, and I'm still not quite sure why. But I know that that's not something hokey or anything, because when we have the wave functions and you apply them to the whole operator, they work just fine. So the hydrogen atom with a single electron is separable, and again, you remember what all of the radial functions look like, right? Yeah, remember what the radial functions look like. Then you've got spherical harmonics, and then we've got spin wave functions. Now, do you remember how, when I started covering like radial this, SPD that, remember I didn't talk about spin? I didn't bring that up till later. Why is that? Any ideas? It's like, oh, I just messed up. When does spin matter? Huh? Yeah, right. It doesn't, I do need to say whether my hydrogen is alpha or beta. It just never matters, right? Because if I'm even doing spectroscopy on just a hydrogen atom, I don't run into any problems, because if it's spin up, it'll just go into the 2p orbital, 1s to 2p, because it'll just stay spin up, or if it's spin down, it'll stay spin down. It just didn't matter. Okay, so then we go into the multi-electron deal, and I represent all of the kinetic energies with these Bell operators. You've seen those before. Coulomb operators, and recall that we start running into a major problem right here, which is that you can no longer separate the radial part into an R1 and a different one for R2. You can't do that, but you do it anyway, and that's crazy. Now, and think about this: if you were, here's a stark example. Let's forget about this absolute value. That can get a little confusing, but just look at this term. If I apply a separated wave function, am I going to get? Is this going to be? Do I have an eigenvalue problem? Is this going to work in a valid eigenvalue problem? If I have a separated, no, it won't. No, it's impossible. Is that right? Yeah, I think so. Yeah, that's the whole problem. You can't. These are not eigenfunctions of this Hamiltonian. So folks, remember that. If this is not separable, this is a mistake. How can it possibly be true that if I write these out, remember that these prevent the electrons from seeing each other. If R1 hits R2, the universe explodes, right? That is infinite energy if those two hit each other. This allows that because R1 doesn't communicate to R2. Therefore, they can hit each other. They're completely independent. They can hit each other, but if it happens, the universe explodes. So these are not valid solutions, and everything that you would think would happen in terms of all of your standard quantum mechanical equations will fail. The problem is we have no other way to deal with this because of our limited, maybe aliens have some other type of mathematics that looks completely different than what we have, and they're like, oh, well, don't you know the solution is fine? I mean, but we just don't know what that is. So ultimately, this doesn't work. Now, last time I was also introducing, actually, let me before I get to this, right? This is spin orbit coupling, and that's where I was kind of rushing last time. Before I get into that, let me remind you a little bit more about, despite the fact that I have the wrong wave functions, the damnedest thing is, if you do the expectation value method of evaluating operators, an eigenvalue deal will fail in this case, but an expectation value will not. It will spit out an energy. And it's just the best we can do. These do tend to be decently accurate. Remember I said they're about 1% accurate. The problem is that that's 1% is about the energy of the chemical bond, regardless. And so when you do this, what you find is you get kinetic energy. And remember, that's always positive. You're going to get Coulomb. That's pretty much guaranteed to be negative. The attraction, that's a little hard to say because the electrons repel each other, that's positive, but the nuclear electron interaction is negative, and that's way, 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 way powerful, right? So overall, these tend to be negative. An exchange, though, which we often call a J, is just the, we have symbols for stuff, right? We get a plus or minus. Now this comes about because of the anti-symmetry of wave functions, which you recall is necessary to prevent you from writing a configuration that is not correct, right? So, so if you do this, therefore, if you write a configuration like this, your wave function becomes 0. So, there's like 1s, 2s. Right. This is all designed to keep you from messing up, from putting 2 electrons in the same state, same quantum state at the same time. If you get it right, you get not 0. So cool. I don't quite know. I mean, as I mentioned before, this anti-symmetry thing is very inhuman. There is no explanation. There's no explanation for this that's physical, because it simply involves you erasing 1s and writing 2s, and erasing 2s and writing 1s in the wave function, and you better pick up a minus sign. We talked about all the ways to do that. So anyway, because of that anti-symmetry, and when you have the wave functions into this giant operator, you basically get this weird cross term, right? Remember, this is like a huge FOIL problem, and this ends up being the cross term. And it's just strange. It just doesn't make any sense. And again, look at what I had said last time about that. Again, I'm still reviewing. So consequences are that let me go back to my 1s to 2s. Let's shine a light on this. And of course, I think you've all been around science enough to know that whenever we express light shining on something, we put a little wave in an energy, and we go from here. I'll pick on the beta electron, from here to here, right? No. Why not? You can't jump from a 1s to a 2s to a p, right? You have an L selection rule, so we're going to have to pick on a p orbital. Okay, so this is still spin singlet. The s still adds up to 0, plus a half, minus a half. But what will happen is it will want to go to a lower energy state, so like this. Sorry, I was doing that one up. I'll just say that the higher energy one spin flips. Okay, so now it's triplet. And the reason is this is a lower energy. Okay, now remember I was saying that the reason this is important is because when things fall into triplet states, they become massively oxygen sensitive. And when they were oxygen sensitive, or oxygen reactive, because oxygen is a triplet, things oxidize. And remember I said last time, you've heard of things oxidizing to death. You've never heard of them nitriding to death, even though nitrogen is overwhelmingly present in our atmosphere. Because nitrogen is a molecular singlet. And so when a singlet runs into an excited state triplet, it doesn't really react. Now, we haven't really covered all this stuff, and unfortunately we won't be able to in this class. But a triplet is kind of like a radical, massively reactive. So if two triplets, two basically radicals react, it's like explosive. So this guy runs into oxygen, bammo, gone. Runs into nitrogen, singlet, triplet, they just don't speak to each other, and so they don't interact. So you don't hear about things nitrating to death. Okay, last bit on this review is to then go over spin orbit coupling. Sorry, I went a little too fast. So what does this do? So imagine that I ask a question based on the beginning of class. Imagine I asked a question that said, what does this do to my wave function? What would be your answer? Now recall that I like to write wave functions as, you know, I've got two R's. I'm going to just say 2 electrons. I've got a theta phi for electron 1. I've got another one for electron 2. And then I would have spin, let's say, just a spin part. Okay, so what does this do to this? A Hamiltonian with parts of the wave function in the same term. Now, how could you separate this, right? Now, remember, separable means that you turn something with a bunch of terms with two operators, say, into one plus the other through some algebraic stuff that we've done that ad nauseum. How are you going to do that with this? How could you turn L dot S into L plus S? Well, maybe you can't, right? So you can't separate these two. You can't separate them. So what's that going to do to your wave functions?
Makes it inseparable.
Which parts? Inseparable. Which parts?
Well, it's L and S.
Huh?
They're not even, L and S aren't even, well, the spin.
Spin. And so the wave function has to be in this. So remember that separability means that you've got you've got this. All of them are multiplied together versus that. An example is like cosine phi e to the I m. An example of this would be like cosine, right? Separated, not. How could you ever untangle theta and phi from that, from a cosine? You can't. Don't sit here and think about it. You can't. Whereas these guys, right, that is the definition of separated. This is basically the definition of not separated. Okay, so now I've got L dot S. What has gotten screwed up? It's relatively simple. What part of the wave functions are now annihilated in our ability to solve them because they're now inseparable due to L dot S? The spin and the Y's, right. Wiped out. Okay, so the crazy thing is, this thing ruins your ability to separate the radial components. But you just do it anyway, right? Now, when you include spin-orbit coupling, it ruins your ability to write separate angular and spin wave functions, but you do it anyway. And because this is the best humanity's ever come up with. Now, if you become a theoretician, I mentioned to you, there are ways of trying to fix that problem. And that, again, that is, you go into grad school to become a theoretician, you start trying to fix this problem. And it is really very difficult, unfortunately. But there you go. So, now again, remember that the main thing is that you would have to have, if we knew what the right thing to do was, we would have wave functions that look like this. But part of the problem is that when it comes to separated wave functions, what's nice is that it has the effect of limiting the range of things that these could possibly be, such that they're tractable, such that you can figure them out. But when they have to be part of like the same function, they're not separable, the range of possible whatevers is infinite. So good luck figuring it out, right? Because you kind of have how many, cosine, how many things could I write like this? I mean, it's infinite. I could cosine theta squared plus phi plus alpha over beta. I mean, I can just sit here and just vomit for infinity time, and I could never still write enough functions that we wouldn't try out and see whether it was a valid solution or not. So it's just not doable. Okay, last bit on spin-orbit coupling. What the effect that is, now let me come back to this, and I'm going to re-represent this. Well, let me show you a little bit about the energy of spin-orbit coupling. And remember, that's not the same as exchange. Don't get those confused. So when it comes to spin-orbit coupling, recall that what it's going to do is, so if it helps you remember what this looks like, recall that this comes about because the electron is whizzing. The electron is whizzing about the nucleus, and what that creates is a magnetic field. Whenever charges are moving, when an electron is moving around the nucleus, a spinning charge creates magnetism. The electron is inherently magnetic. So you've got two magnetic fields, one from the electron's motion and one from the electron. So the fact that it's whizzing gives me an L B field, but the electron is also spinning. So this is from S. And so it has a magnetic field. So this is the magnetic field from spin. Now, is this bad or good? Now, before you answer that, let me draw the L magnetic field. Now, let me draw the B. See, what could happen is the spin could go the other way. And these, of course, are vectors. Okay, which one's bad and which one's good? Remembering that these are magnets. Back there, yeah. Now think, again, quantum aside, I got two magnets. Right? And, bad? Which one? Which one's bad or good? Which one's bad? Bad. North, right? Bad. So
left one's bad.
Bad, right. Bad. Good. So it's energy raising, energy lowering, right? So magnets still work the same way as you thought before. Okay, now the effect of this is, and this is the part I was really rushing, so I felt kind of bad about this, is we like to think of a wave function as being either pure singlet or triplet. Okay, now, I'd have to maybe, if anyone ever came by office hours, I could show you mathematically how this works. It is kind of interesting. When you can no longer separate these wave functions, although we have no idea what the functions truly look like, it's just way too confusing, it turns out that one way to deal with it is to bleed triplet wave function character into the total wave function. So what I'm drawing here is the wave function that we'd like it to be, but spin-orbit coupling basically bends the vector a little bit sideways. So now the wave function is, let's say, 90% singlet, and I'm just making that up, plus 10% triplet. Now again, I know it's kind of hard to see this, and again, I really don't have the time to explain mathematically why, but the fact that these cannot be separated into different wave functions, if they're separable, then you could represent them as just like x and y. I mean, that's what separability is, right? Instead of an x and y, I have r theta c and spin, but like x and y, I can represent them as different orthogonal axes on a graph. Now, the effect of you can't do that is, again, unbelievably confusing, so confusing that even mathematicians, Albert Einstein, Stephen Hawking, never could figure this out. But the effect is that it's as though they mix together. So, and I'm just kind of telling you that. Okay, so what? All right, let's go back to this guy here. Let me just redraw that. Okay, so we go from a ground state that's like this to an excited state. And let's say that we want to call this singlet. Now, we want to call that a singlet state. Now again, you now know that that's really not fully true. It's like 90% singlet. But the triplet is slightly lower in energy. And now we've gone from a 90% singlet state to a 90% triplet. So let's just call them singlet and triplet. Now here's the thing. How did this electron spin to begin with? Spin flip. Now recall that one reason that we went from up down to up down, the reason that the spin is preserved is light has no S. Light has no spin, no angular momentum for which we call S-type angular momentum. It has L, but no S. So remember that we've covered this for a while. Photons are doing this, right? Remember that right and left circling polarized light. Light is actually spinning as it turns. We covered that a long time ago. That's L-type angular momentum. That's why the electron has to go from an S to a p orbital, because you have to conserve that L. Light has no S-type angular momentum. Again, we don't know what S is anyway, right? So I guess that kind of makes sense. So that's why you go from S to P, because of the L of light, but the spin stays the same because light has no S. Okay, now why would the electron then flip on its own? The answer is spin-orbit coupling. Spin-orbit coupling means that it's like a gateway to slip from one state to another, because you're kind of been into its space a little bit. All right, now you've gone from the ground state to the excited state singlet, and here's the triplet. And again, you slipped into that triplet state because, for one, it's lower energy. Number two, you have spin-orbit coupling. Otherwise, you'd never be able to do so. And then what happens is, eventually, you're going to relax to the ground state by phosphorescence. Right? So you've heard of that. Now, you know the difference between fluorescence and phosphorescence, right? Remember that these are phosphors in our light bulbs. They're mostly composed of somebody's trying to find the right one. These are mostly composed of okay, whose is it? It's going to go nuts. One of you has to fess up. Whose is it? Might be from the guy's head.
Yeah, it could be from the last class.
Last class? Yeah. Should I? Is it someone calling? Should I answer it?
They're pinging it with your watch.
Does everyone know how to turn this up? There we go. All right, anyway. Okay. Hopefully that was kind of fun. So now you folks know the difference between phosphorescence and fluorescence, right? Right. So phosphors are in our light bulbs. It's mostly cerium. It's like cerium in TiO2 or something. No. Cerium in alumina, Al2O3. Add cerium, and that's mostly what's in here. And that is a phosphor. Fine and good. That differs from fluorescence from a dye. So for well-known dyes like fluorescein, maybe you've heard of that, rhodamine, maybe you've heard of these dyes before. I've mentioned cyanines. What happens is when they go to the singlet state, if they stay in the singlet state, they'll fluoresce. And that's where you get all your dyes from. But things that are in our light bulbs are, they kind of easily go into the triplet state, and those are phosphors. The way you can tell is that you look at the lifetime, and these live for the tens of what I want to say microseconds, micros 10 to the minus 6. Fluorescence goes tens of picoseconds. A pico is 10 to the minus 12. So whenever you have a fluorophore, what we do is we time resolve the emission, and you can actually do this with just a little, so it's like I got a little cuvette and I hit it with a laser. You actually do this in PChem lab. It shines light, and then you have a photodetector connected to a, God damn it, what's it called? What are those little machines that you see little waves on? A oscilloscope, right? You have it attached to a oscilloscope, and you can actually resolve between these two. And anyway, yeah, I guess that's all I really wanted to say about that. And I also noticed that, now remember I was mentioning that cerium in aluminum is a very common phosphor. Notice that cerium light or heavy? Periodic table off the top of your head. I mean,
heavier?
Heavier, right. Remember, spin-orbit coupling scales with mass. So heavier elements are more likely to enter the triplet state because they have higher spin-orbit coupling. And that has to do because the constant of proportionality. I wrote out the full thing last time. I'm still actually reviewing, by the way. I wrote out the full spin-orbit coupling Hamiltonian. It's rather painful, so I just put a little constant here. That's actually mass dependent. So for heavy elements, spin-orbit coupling becomes incredibly strong. So anyway, well, I mean, folks, this is literally it. We are literally done with all of this multi-electron. Oh God. I think I know which button to press. The thing is, the person should feel bad because I could probably blow up their phone. Anyone have any questions before we, I mean, look, this is literally it, just completely moving on. Any questions about any of this before we do so? Alrighty, so, okay, I hope the world of quantum, no more quantum. That's it. You are as educated as an undergrad in quantum. As an undergrad will ever be. And if you go in, okay, if it does it one more time, I'm going to have to just take it outside. Daniel Kerrigan, hey, if you found this phone, the charger goes with it. I left it during my chemistry exam.
Do you want to take it to the student center?
Well, we're almost done. We only got 10 minutes of class left, so let's just hold off. I think hopefully it won't happen again. I'll take it to the student center next. Anyway, I got class after this myself. Okay, so for the next two lectures, for what I've got left of today, I'm going to just, this is all very descriptive until we get to kinetics. Really only two lectures. Here, let me write this down. The EM spectrum. So I'm going to write down the entire electromagnetic spectrum. And this is the kind of thing that you folks, kind of college educated in science, you should know this kind of stuff. I'm also going to tell you cool stuff about lasers and just about synchrotrons. So this is an analytical class, and so I don't really want to turn into analytical class. Remember that spectroscopy is, you know what the dipole operator is, but it's its own thing. So I'm not going to turn it into that. So I'm only going to spend two lectures. One just today, cover the electromagnetic spectrum, tell you where that cell phone works. And next time, I want to go over, like, not just the stuff you learned in analytical, because you've already covered that. I'm going to tell you about, like, way the more advanced stuff that, like, basically isn't in your analytical textbook if it's more than a few years old. So, and I'll try to make that as fun as possible. And I'm sure I'll put that on the final as some extra credit question or something like that. Regardless, the electromagnetic spectrum. So I'm going to have to put this in two different units. EV, electron volts, is what physicists used. It's generally quite useful at high energies. And of course, chemists tend to use not meters, but wave numbers. But anyway, I'm going to put it in terms of meters because that makes more sense in terms of the wavelength of light. The first part of the, I mean, there's technically no lower bound to how low you can go, and there's no upper bound to how high you can go, but there's some practicality to this. Like, I don't think I'm going to create a 1,000-meter photon generator, because I'd have to have something 1,000 meters, and that would be kind of difficult. Regardless, this is what we call the radio. This is the radio region of the electromagnetic spectrum. AM is at, not that anyone listens to that, AM is at low energy, FM is at high energy, and in between is where TV signals, I guess they still transmit TV. I mean, everyone has cable now, but this is where it's nestled in between, and guess what? Cell phones are slightly to the left, a higher energy of FM radio. Now, one thing you should know is that the federal government controls airwaves. You cannot just build a tower, your own cell phone tower, and start transmitting your own radio or TV show. If you did that, and people have tried, welcome to prison. They're going to send you to prison for a really long time. For some reason, this is something the government goes crazy over. They absolutely have unbelievably strict control over your transmitting information through the air. If you do it, they will catch you. They have teams that will come out to an area, triangulate your position, and arrest you immediately. I have no idea why they're so nutty about this. I mean, they kind of, one thing is they don't want people transmitting their own political things, like take over the government. Now, I kind of get that, but why they go so far with this, I don't know. Another thing to note is that the government owns the, they call this, they own the bandwidth and they sell it. So the government, I believe, has already done so. There was a large amount of frequencies in the cell phone region that they owned and wouldn't let anyone use, and they sold it at a profit. The problem is that that's letting the genie out the bottle. As soon as they sell it, they can't buy it, it's gone. So I thought that was actually a little short-sighted. Okay, now we get to the 10 to the minus 3. So now I'm at a micrometer range. And in terms of energy, my energy is now increasing. Okay, so this is the microwave. Microwave region is also the radar. If you've ever got a ticket, it's also the radar range. So the first microwave, did anyone know the name of the first microwave oven, what the brand name was? It's called a radar range. So the 1950s, when they first started coming out. It wasn't until the 80s when I was very young that it started becoming common to have microwaves. And to differentiate themselves, they stopped using the radar range brand name. Again, it was just a brand name. Now, this is the area, you know, one thing about this is if you look at transitions of molecules and atoms that absorb energy, you won't find any that work in this region. This is why we use this for television and radio, because it goes through walls. Another thing that the government, the military, is very interested in, you know, night vision, right? They want vision that works in this range. Now it's a little hard because if you use, say, 1 meter photon, you can't observe, you can't, your resolution's 1 meter. So in terms of discerning a person who is about 2 meters, it doesn't work. But it looks through walls. So this is a big area for government, is to work in these regions to build detectors. I mean, again, they have problems in terms of discerning, say, a soldier from a different soldier. But it goes through walls, and you probably can see a tank or a missile. And you can see that deep through a building or the ground because light just passes through material because materials don't absorb it. Now, when you get into this range, you get your first absorptive events. This is due to rotation. Okay, so molecules start absorbing, this is enough energy for molecules to start to get interested. They start absorbing it. And the transitions you observe are rotations. So how does your microwave work? And don't tell me by turning it on and plugging it in that yes, that is necessary.
The water
Energizes
molecules.
water molecules.
Right, causes them to, no, specifically that is actually wrong. Cause them to rotate. They're rotating faster, right? It's also relatively safe and easy to generate that light. Okay, so now that we've gotten into a molecule starting to interact, then we get to 10 to the minus 6. Okay, so millimeter, now micrometer, and EVs along 1. And that's the infrared region. Okay, now what molecules are still interested? What do they do? Right. Vibrate. So you will see people selling toasters, little tabletop heaters that are actually, they'll even say this is infrared. And all they have inside of them is a giant glow bar. So there you go. Now, actually, I meant to tell you, there's actually this really interesting thing that occurs right here, which is called a libration. So you will not see this in almost any textbook or analytical or physical otherwise. So again, molecules will rotate, they'll vibrate, but in between is this libration thing. What happens is, let's take water. At any given moment, say 2 water molecules are like, they're connected. They kind of energetically paired. This is transient, but for a moment they're kind of like they're together. What happens is they're bumping into other water molecules. They're like in a solvent cage, even though they are the solvent, and the molecules right next to them feel the same way. So in this very brief moment, when molecules are kind of hooking up, you actually can kind of rattle them as like a pair. And that's what we call a libration. So you do get absorption in between the microwave and infrared region, but for a very, very strange reason that you'd have a hard time writing a wave function to describe that. Okay, now you get into a very interesting area. So hold on. Okay, so you can imagine I'm getting oddly specific. And this is red. You're now in the visible. Okay, but what's more interesting here, this is the dead zone. Another dead zone, where, guess what, the military is heavily investing detectors that work into this. So from about, let me work in wave numbers, from about 4,000 wave numbers, that's the infrared. The visible kicks in around 10,000 wave numbers. Sorry, that's just what I know off the top of my head. You have nothing. That's the dead zone. Now, again, the thing is that vibrations, this would be like an H2 vibration. H2 doesn't absorb infrared light because the dipole doesn't change. Anyway, I'll talk more about that next time. And then this is where you start to get electronic transitions. Vibration, the next thing on the energy scale is electronic, hydrogen 1s to 2p and all that. But in between is a gulf that nothing happens. And so you're dead. So light at these wavelengths would go right through. Okay, real quick, I see you're chomping at the bit to go through, because there's not much else to say. When you get to 400 nanometers, that's 4 times 10 to the minus 7, you've got blue. And that is about 3.1 EV. That's kind of easy to understand. These are all valence electrons, transitions. Then you get to the UV. This is UV light. These are also valence electrons, but very damaging because they impart so much energy into your skin that they'll rip your DNA apart. And then you've got the highest power that people have ever made in terms of photons is around 10,000 eV. And molecules absorb this light. It's due to core electrons. So you get valence electrons absorbing light. Again, you know, molecules, outermost homo-lumo transitions. When you have X-ray, let's say you have a big heavy atom like copper, cadmium, what happens is it's still an electronic transition, but it's from the 1s. 1s orbital to wherever. And the way you make, next time I'm going to tell you how we make light at that wavelength. Instant cancer, instant death if you get in front of this thing. It costs $2 billion, by the way. So Argonne National Lab has a synchrotron that makes light at this wavelength. It costs $2 billion to do so. But it was thought to be so important for materials characterization that that's what we did, spent $2 billion. All right, so time's up. Next time review.